We continue with the next speaker in this afternoon. So the talk is a simple derivation of Bohmian Mechanics by Nino Zanghi.
Yeah, thank you. Thank you very much to Olympia for the invitation here. It's a wonderful place, it's a wonderful town. And I'm really happy to be here. That's not the title of my talk. That is what my talk would have been. A very short one, 30 seconds talk. This was done by Dustin Lazzarovici or Nicola Vona when they were PhD students in the math department in Munich. It's a nice video, and it's the simplest derivation of Bohmian Mechanics and I'm aware of. No, I mean, my idea would be to stop and go and we go to have a, but okay, I promised to give a talk, so I will give a talk. Since I'm a physicist, I learned that I'm allowed to criticize physicists, while philosophy cannot do that. Actually, I want to give a physics talk. I mean, I'm a physicist, a theoretical physicist. I devote a large part of my research to Bohmian Mechanics, foundation of statistical and quantum mechanics. But okay, so my talk is a bit difficult, and for somebody it will be boring, for somebody it will be too brief. My idea is to give an introduction to Bohmian Mechanics. I mean grounded in the usual sense, not that name that nowadays in metaphysics is very popular. I mean just in the normal sense, okay? And two things. This talk is dedicated to Alberto Rimini. Rimini died two months ago. He was a friend. He was one of the leading experts in foundations of quantum mechanics in Italy. And so that's I want to remember him. I mean, leader of doing this one with people like I'm trying to do, doing research on foundations in a physics department. I mean, doing really physics, doing computation, proving theorem, all these sort of things. And what I'm going to report is a joint work with Detlef Duhr and Shelley Ghost and many other people that has been going on for the last 30 years. So a long period. I want to say, before entering into the talk, the real talk, I want to comment on two keywords that are in the title of our international workshop: identity, indistinguishability, non-locality in quantum physics. Okay, identity and distinguishability, I will comment on that later on. Concerning non-locality, I just transformed into formulas what John Bell says in his preface, the preface of his collection, Speakable and Unspeakable. He says that in his page, he never wrote what he wanted to write, namely how to express his theorem. And he gave an indication how, say, oh, that's very easy, you should do this way. And that's the way that I recall what Bell's understanding. I should say here, and in some other places of my talk, that I always under the assumption that results have, that measurement have one result. So in this sense, I exclude theories like many words. And I will not mention Giardabio, even though it's a theory that I like. Before I mention Rimini, Ghirardi, Rimini, Weber. That will also not enter in my talk. We just concentrate in Bohmian mechanics, and when I make general assumption, I assume that measurements have one result. Now, what Bell says in that preface of the book, he said that what he proved was a two-line argument. The two-line argument is that the first part, A, is the EPR certified paper. Quantum mechanics plus locality implies something, which I call C. We don't need to enter into the nature of what C is because it doesn't play any role what really C is. Then I will tell you, everybody knows, is hidden variables, local hidden variables. The 64 paper implies that, says that quantum mechanics imply no C. That means the same C's that were derived in A are, quantum mechanics imply that they are not existing. So Bell says the conclusion is quite obvious. There is a contradiction between locality as such, and not merely in some special cases of local theories, and now experimentally confirmed predictions of quantum theory. That for me is similar to the video that I gave before, is Bell's idea in one shot. And this to me seems quite logical and compelling. In a conference, I remember an expert on quantum information that I will not mention, he said that, oh no, but Bell's theorem has nothing to do with EPR. When I get this objection, I point out to the title of the paper of Bell. The title of paper of Bell is on the Einstein-Podolsky-Rosen paradox. Okay, now I will enter into the real talk, this overview of Bohmian mechanics. And I choose a path. I want you to explain why, according to my understanding, there is some continuity between the book that Bohm wrote in 1950 and published in 1951 and the article on what he called the interpretation of quantum theory in terms of hidden variable, written in the 51 and published in 52. There is discontinuity between these two works. And the discontinuity is obvious to everybody, to the extent that they know the content of the book and the content of the article. The content of the book is just a clean presentation of orthodox Copenhagen interpretation of quantum mechanics, one of the best ones. For me, when I have to give advice to students where to learn, I give Bohm or the Landau-Lifshitz as one of the best presentations of a standard view on quantum mechanics. Now, so I say there is, of course, this continuity, but there is also some continuity. And my idea is to emphasize the continuity between these two. I want to comment on the role of a wave function in the description of quantum experiments. When I mean quantum experiment, all sorts of quantum experiments, starting with the earliest experiment showing the wave nature of matter, the Davis and the Germer. Then I have the classical two-slit experiment. And let's say also the Stern-Gerlach is there, just to remind us that that was an experiment that showed us a non-classical property, namely spin. Now, the role of a wave function is to govern the statistics of a result of quantum experiment. So, I mean, this is something that Bohr never denied. Actually, he emphasized that in standard quantum mechanics, a complete description of a system is given by some classical variables, and for instance, the points on the screen, and by the wave function psi, that is by the pair, which I call z psi. Apart from the notation, this is what you find in the Landau-Lifshitz, what you find in the many orthodox presentation of quantum mechanics. The assumption of classical variables describing macroscopic objects. And for example, thinking of a two-slit experiment, you have an accumulation of dots on the screen. So the classical variable are the macroscopic positions of the dots. And the dots accumulate when n is getting very big in a way that they are well described by the square of a wave function taken at the time that the particle is on the screen. And now a quotation from Bohr. Bohr was saying, must above all be recognized that however the quantum effects transcend the scope of classical physical analysis, the account of experimental arrangement and the record of the observation must always be expressed in common language, supplemented with the terminology of classical physics, which are summarized by my z, these classical variables. And actually, if you consider the beginning of a Landau-Lifshitz book, you find a proof that observables are described by operators. And Landau explicitly says, let's describe the apparatus by classical variables. Let's assume that the interaction between the system and the apparatus is unitary. And let's make an assumption about the sort of experiment we have. I mean, this has to be measurement-like. And Landau, that is reflecting a paper that Landau wrote with Pyers in the 30s, assumes something that he called predictability. I will not enter into the detail what predictability is, but by setting this condition, then he shows that the statistics of the result of measurement is given by self-adjoint operator in the usual way, with the rule for the mean, the rule for the second moment, and so on. The assumption of predictability is not so physical like it seems, was criticized by Schrödinger. And a more physical assumption is that of reproducibility. When you have an experiment, that means an interaction between a microscopic system and an apparatus, if you demand reproducibility, you are demanding that if you repeat the experiment after it has been performed, then you get again the same result. And now you can prove with very high generality that you get exactly a self-adjoint operator governing the statistics. So there is no need of following Bohr in his very philosophical and strange views, but there is a way of presenting standard quantum mechanics in a very understandable way. That's what I usually do in my course. Then I cover the standard argument, but I don't try to put any mystery when there is no need of putting mystery. Classical variable. Yeah, there is a problem with that. And this problem is a problem that Bell emphasized in many of his articles. Problem with classical variables. And the problem is, what is the boundary? Before we were talking about, oh, quantum mechanics does not apply to classical objects. Yes, but where is the boundary between the speakable classical world and the unspeakable quantum world? That's the meaning of the title of the book of Bell. And this is the core of the measurement problem. I mean, this is much more serious and much deeper than the problem of Schrödinger's cat. Of course, these are related, but this is much more general and to the point. Now I'm collecting here slides from one of the last talks that Bell gave. And this is just a slide that he used. He said, there is a fundamental ambiguity. Nobody knows what quantum mechanics says exactly about any situation. For nobody knows where the boundary really is between wavy quantum system and the world of particular events. This is the problem of quantum mechanics. It's no problem in practice, because practice is not accurate enough and maybe never will be. And in practice, I've been using quantum mechanics all my life, but that's only if you think that here there is an issue which is not a practical issue. Is an issue about an ambiguity at the fundamental level. And so I want to present Bohmian mechanics as a way, it's not the only way, as a way to make quantum theory exact. There is already a dualism in standard formulation according to Bohr and Landau-Lifshitz and standard Copenhagen, the use of a wave function and the use of classical variables. The classical variables are macroscopic, so they depend on a choice of a boundary between the micro and the macro world. What is the simplest way to make precise such a theory? Is to abandon the macroscopic character of Z and to say, okay, I introduce an additional variable which represent the positions of the bodies and of the particles, and which is defined on all scales. And the macroscopic variables are a function of a microscopic configuration. So I can have a picture of what is going on in a system very close to a classical one, and the laws of motion are different. That's all. And the macroscopic variables, like the pointer position, the thermodynamic value, are functions of the microscopic ones. That means the configuration. The slide that I took before were from, I said, one of the last talks that Bell gave. The title of that talk was Towards an Exact Quantum Mechanics. It was a conference in honor of Schwinger, and Bell started the talk saying, praising Schwinger for the wonderful accuracy of QED, for his result on the anomalous magnetic moment of the electron, and saying, okay, we should have a better formulation which has the same wonderful numerical accuracy, but at the same time is also precise as a conceptual precision, not only numerical precision. And the notion that Bell introduced, and I'm very attached to it, I think is a good notion, has some philosophical good implication, but I will not say anything about philosophy in my talk. Maybe tomorrow Mikael will say more on the philosophical side. I want to say that the notion of beable, that it was introduced by Bell, was a useful physical concept. And the idea is not to base a physical theory on the notion of observable, because, like he was saying, is not easy to identify precisely which physical processes are to be given the status of observation and which are to be relegated to the limbo between the observation and another. So it could be open that some increase in precision I lost the track, might be possible by concentrating on the beables, which can be described as in classical terms. There is some irony in the use of beables. In one of the papers, they say, oh, once Zumino suggested beer, but then beer is not so good, and then being is too philosophical, so let's have beable. So physicists are so often used to observables. Let's use beable as denoting what could possibly be there, according to the theory. I mean, nobody say that theory are eternal, not at all. So it's not so metaphysical like it may seem, this name. But observable must be made somehow out of beables. And the theory of local beables should contain and give precise physical meaning to the algebra of local observables. And here, again, I emphasize with Z, the classical variables are function of Q. And I see continuity between an orthodox understanding and the Bohmian understanding. If you are not too attached to the philosophy of Bohr, but you just look at the theory as a physicist, then the demand of higher precision is not such a strange demand, and so you end up quite immediately with Bohm. I repeat, it's not the only possibility, but to me seems very natural. And for me, so it's not so mysterious that in less than 1 year, Bohm wrote a wonderful book on the standard interpretation, and then he wrote that paper in which he was presenting an interpretation in terms of hidden variables. The equation of motion. The equation of motion are this one you take on a non-relativistic level, just the Schrödinger equation. And the guiding equation is written in that funny way. You can say, why you don't simplify numerator and denominator and you divide by psi star? I didn't do it because by defining the velocity in this way, I allow for psi having internal degree of freedom. And if you have spin, spin will be in the wave function. The wave function will be spinor valued. And nobody ever will say the spin is not real. Spin is in the wave function, and I think of a wave function as being real. So, I mean, I'm totally attached to the spinorial representation, which are there, and their role, the role of a wave function, is of generating the motion of Q. You can arrive to this equation in very different ways. You can arrive to it from de Broglie hypothesis, the one of relating wavelength and velocity, simply extending that relation, which is true for a plane wave, extending to a general wave, and assuming that that relation, the Broglie relation, will hold locally in a small, for each point in a small neighborhood. And then you get to that guiding equation. And there are many ways through symmetry. If you just demand that the theory be Galilean invariant, you get that equation basically from the usual symmetries of the Galilei group. Now, here I wanted to say something now, a bit more advanced, and stay there for no more than 10 minutes. Because this was mentioned in this meeting, and I want to say something about identical particles. Now, the traditional view is not just a view that Decio gave to us a few days ago. It's a view that I learned as a physicist, is that if particles had trajectories, they would automatically be distinguishable. That's what my teacher was saying. The trajectory would define which particle time t is which particle time 0. It is exactly because particles do not have trajectories that they can be indistinguishable or identical. In particular, identical quantum particles somehow more identical than identical classical particles. That is a summary of what was the creed of my teacher or many, many physics professors. Now, this to me leads a sense of mystery. I don't want to be offensive at all, but for me, this idea that Decio put forward of non-individuals or quasi-individual or quasi-sets, to me doesn't make any sense. And maybe I'm too naive, I'm not enough open-minded, I have no idea, but to me doesn't make any sense. So I have to be honest. And first of all, I want to say that Bohmian mechanics in R3n, that means the equation that I gave before, is a counterexample to this claim in the sense that take the wave function, either symmetric or anti-symmetric, and then fine, everything works. No problem whatsoever. There is compatibility with quantum statistics, despite the existence of trajectories. I will be already satisfied with this. But something more can be said. And the more is that I can use Bohmian mechanics to explain the quantum statistics. And it is work that we did in the 2004, 2005. We wrote several papers about this. Using ideas that were known to the people doing path integrals. And it's clear, people doing path integrals give prominence to what is going on configuration space, because the path integral is defined there. And in particular, the topology of configuration space is essential for the characterization of the path integral. Well, the same thing happened in Bohmian mechanics, where you have a dynamics. You have more than in the path integral approach. You have a deterministic dynamics defined on configuration space. Now, what is the natural configuration space? The natural configuration space of identical particle is just this one, what is above, and not this one. This one means to give names to the part. If you have just dots on the plane. And what is the mathematical entity which describe a set of dots in the plane without any label? It's the notion of set, not the notion of vector. The notion of vector contains information about particle 1, particle 2, particle 3. No, you should use sets of n elements in Rd, R3 if you are in physical space. So that is the totality of 1, 2, 3, 4, 5. The totality of 5 dots, of a set of 5 dots in physical space, is the configuration space of identical particles. And this configuration space, you can use it in classical physics. That's a point that Lenas and Mihai make. You can use it, and then you see immediately a resolution of the so-called Gibbs paradox. But in classical physics, does not have any dynamical implication. In quantum mechanics, it does. And in particular, what plays an important role is the fact that that space, as soon as you take out the singular point are the collision point, when you put two points on the top of one on the top of the other, exclude them, then becomes a smooth manifold. And is a smooth manifold which is not simply connected. And that's the space on which live a wave function, naturally. And I should say, really naturally leaves the particle, the configuration. The configuration moves on the natural configuration space. Now, if you start with a wave function on the natural configuration space, you immediately have bosons. Then what about fermions? Now, fermions comes immediately as soon as you realize that you want to have a well-defined dynamics, that means a well-defined vector field on the natural configuration space. But this can be generated by a wave function living in a bigger space, what mathematicians call the covering space. If you have a circle, the covering space of a circle is the real line. And when you are covering with the real line the circle, you have a boundary condition when the main distance repeats. These boundary conditions are connected to the representation of a permutation group in 3 dimensions, and you get immediately the fermions associated to the odd representation. For simplicity, assume that the wave function is scalar valued. So that means the only representation that you are using are the characters. And the permutation group are 2, +1 and -1. The -1 will correspond to fermions and +1 to bosons. So it's very natural. If you go to higher spin, the situation gets a bit more complicated. But still, I don't remember whether in this paper or we wrote several papers about this subject in these years. We could prove an exclusion of parastatistics. Namely, we could prove that if you have spin, also, you have to exclude the intermediate statistic, the Young table that Nathan was mentioned a few days ago. You have a nice argument to show. Of course, you don't have, at this non-relativistic level, you don't have an argument for complete association between statistics and spin, but we know this is a relativistic effect. This is a root. There are another very interesting paper which developed mathematics that can be applied to the Bohmian cases, this one of Linus and Mirain, that treat not in terms of covering space, but in terms of a sort of gauge field. And but I will not enter on this technicality. That was my first more advanced topic I wanted to cover. The second one is what I'm doing now, what I've been doing for the last 2 years. I felt the need of spending 2 minutes on what we are working with Shelley and Detlef, and a PhD student of Detlef in Munich. We have been working a lot on a complete relational formulation of Bohmian mechanics. By complete relational formulation, I mean a formulation in which there is no absolute space, there is no absolute time. And this has been in philosophy a debate for many centuries. But then there was no clear mathematical paper saying how we should construct such a relational theory. The first one, to my knowledge, is the paper of Barbour and Bertotti, which really gave a clean indication how to go. And here this is the picture. The picture is, suppose you're considering just 3 particles. So 3 particles are forming a triangle. You want to have a theory in which the orientation of a triangle, here or there, doesn't matter. The scale of a triangle, I mean, can be small, can be big, doesn't matter, because you are thinking of a theory that should hold on the universal scale. And so you are following in the mathematics Leibniz when he will say, oh, nothing will change, it's overnight, the universe will double, and everything will be shifted from one place to the other. But there is an incredible nice mathematics arising, because then you get that the absolute configuration space becomes a fiber bundle on the natural space. The natural space is the space of shapes. And there, the nice thing is that you have to construct the dynamics on the natural configuration space. All you need is a measure of distance between shapes. The paper of Barbaro and Bertotti introduced what they call best matching, and the best matching corresponds to a Riemannian metric on Q. And this Riemannian metric on the natural configuration space can be obtained by a suitable group invariant metric on the absolute configuration space. And the nice thing is that you can define a free dynamics. I'm talking now classical mechanics, a free dynamics on Q. And when you look at this free dynamics on Q, it appears to you as an interacting theory. So it's a very interesting formulation of classical mechanics, first. Second, it's promising for the quantum extension. This is what we have been working, because you all the quantum structure depends basically on the metric also. So the geometry basically fixes everything. Surprisingly, there is not so much work done on this. People attack this problem using direct quantization or Feynman path integrals. The road that we are following that is similar to what we did for identical particles, namely to have a well-defined Bohmian mechanics, it is giving to us a nice Schrödinger evolution of the width type, that means stationary, with some mathematics more complicated than I expected. But we are almost finished. And for us, almost finished means another 2 or 3 years. Okay. The goal, that's why we started. We started because we had in mind gravity. We wanted to have an extension of Bohmian approach to quantum gravity. And what becomes this in quantum gravity? It's just the old framework that was put forward by Wheeler. The absolute configuration space becomes the space of 3 metrics. The group is the group of 3 diffeomorphisms. And in this way, you get an intrinsic natural space. And you can think, in the classical case of Einstein equation, as a sort of geodesic motion in this infinite dimensional Riemannian space. Is everything a bit vague mathematically, not so precise, but there is a way of making sense. And since we saw in the finite dimensional case that once you have the metric structure, you have everything, because you have a Laplace-Beltrami in the quantum case associated to the metric, then we hope that we can make some progress also there. Now, how much time I have? 20 with the discussion. But we started 5 minutes late. 25 minutes with discussion. Okay, then it's fine. That's fine. Okay. Now, there are many implications of Bohmian mechanics. Okay, you can get familiar macroscopic reality. I mean, you can have a classical limit. You can have an explanation of quantum randomness. Heisenberg principle follow. And these are all in our papers. I mean, of course, in this brief talk, I cannot comment on that. If I have time, I will comment a bit on the wave function of a subsystem. But most of all, I want to comment on the agreement with the prediction of quantum mechanics whenever the letters are not ambiguous. Not ambiguous, I mean situation in which quantum mechanics is not clear what is predicting. Let's say the time that the particles spend in a region, the time needed to go from here to there. These are not clearly well defined in standard quantum mechanics. I'm not saying that cannot be, but are not so natural, like the self-adjoint operators. Maybe they could involve more complicated notion of observables like POV and this sort of stuff. Now, here is a mathematical property of a Bohmian system. The mathematical property is that the Schrödinger evolution and the Bohmian evolution, I mean the motion on configuration space, are compatible in the sense that if you have a rule to generate probability distributions associated to psi, you can do it at time 0, you construct a rho psi, given, I mean, you have a certain fixed rule to construct rho given psi. Then you can let evolve psi, apply the same rule, and you get rho psi t. Or you could evolve directly the rho, the density, by transporting along the flow. In general, for a general rule, you will never get the same result. But if a rho is psi square, you get the same result. We call this nice property equivariance. And equivariance is playing, from a mathematical point of view, the same role that invariance plays in the analysis of dynamical systems. The quantum equilibrium hypothesis is, think first as a, like you think of Gibbs hypothesis, that when a system is in thermal equilibrium, distribution is given to e to minus beta h. And the idea, and this in this case will be the Bohn's rule, is an hypothesis. And our first paper on the subject in '92 was aimed to give a proof of this hypothesis in the same sense in which Boltzmann gave a proof of Maxwell-Boltzmann distribution for a free gas, or a weakly interacting gas. Now, here the story can be said in a very simple way, or in a very complicated way, which is more what we actually did. But the simple, I will give you just the simple story. The simple story is we could regard the quantum equilibrium hypothesis as an additional postulate on the initial conditions. Then, by equivariance, the mathematical property that I described before, it will be preserved by dynamics, so that we get, we obtain quantum equilibrium, that means psi square, for all times. As a consequence of this, we obtain the conclusion that Bohmian mechanics made the same prediction as does orthodox quantum theory for the result of any experiment, not just position experiment. For example, an experiment measuring spin. I give you only a flavor of a beginning of a true story. So I give you only the beginning of a true story, just a flavor. Is our work of '92, which is a rather long work, and is a technical work, we proved theorems there, was to show more or less what you do in classical physics with Boltzmann, doing for this case. Before I mention how Boltzmann proved that Maxwell-Boltzmann distribution is the typical distribution for a gas in equilibrium, here we do the same sort of analysis. And for us was very relevant a comment of Bell, and says that is basically criticizing the simple story that I gave you. I mean, the simple story leads you nowhere. Why? Because for instantaneous macroscopic configuration of the pilot wave theory, the pilot wave theory gives the same distribution as the orthodox theory, insofar as the latter is unambiguous. I told you before, this is a trivial consequence of equivariance. However, this question arises. What is the good of either theory? Giving distribution over an hypothetical ensemble of words when we have only one word. So that's the serious problem that we tackle, namely that why the simple story cannot work. Because what we want to explain the statistical patterns in a single history of a word. To do an ensemble average over a totality word is sort of irrelevant. A single configuration of a word will show statistical distribution over its different parts. Suppose, for example, this word contains an ensemble of similar experimental setups, like above. It follows from the theory that the typical word will approximately realize quantum mechanical distribution over such approximately independent components. The role of a hypothetical ensemble, let's say the psi square of a total system, is precisely to permit definition of the word typical. And what we succeeded in is proving a law of large numbers that show exactly that. Namely that we have convergence of statistics, which is the left-hand side, to the theoretical prediction. Psi of q is the wave function of the subsystem. And is a non-trivial law of large numbers in the same sense in which is non-trivial the law of large numbers that Boltzmann proved. Okay. And now, given this, you have a way also to make precise what I said at the beginning. In this setting, you can explain why the operator arise. It's not so different from what Landau Lifshitz do, but what? What is the basic difference? Is that in that theory, I will call it rational Copenhagen. In rational Copenhagen, there is no dynamical evolution for the classical variables. And it's not even clear when something is a classical variable or is a quantum variable. So here you have a complete precision, namely you have the Q variable, the microscopic variables, and you have a well-defined dynamics. And so the theorem is even cleaner than the one of Landau-Lifshitz. Now, in one of the papers of Bell, he said there is a final protest. When the cogency of Bohm reasoning is admitted, the final protest is often this. It is all non-relativistics. This is to ignore several facts. To ignore that Bohm himself, in an appendix to one of the 1952 paper, already applied this scheme to electromagnetic fields. And the application to scalar field is straightforward. However, until recently, to my knowledge, no extension covering Fermi field has been made. Such an extension will be sketched here. He gave a very sketchy presentation of a possible theory for Fermi field on a lattice. Now, we did many works on that, exactly on how to exploit Bell idea to extend Bohmian mechanics to quantum fields. And that is a sort of very, very old work, 2004, that seems like. And these are formulations in which particles get created and annihilated. That means it's not anymore deterministic a theory. Tomorrow, I think Michael will say something about another possibility along similar lines. That means to explain why it's not true what usually people say, that the theory does not cover quantum field, that the theory is not able to account for creation and annihilation. And concerning relativity, we also made, I didn't put the reference, but also work on in which sense, I mean, even adding an additional foliation is much less unrelativistic, is much more relativistic than usually people may think. Meaning that you can, if you have a quantum theory in which you have a wave function, the wave function is already a non-local object. And given the wave function, you have a way of generating the foliation. So it's a dynamical choice of a foliation, in the sense that it's not you put from outside. Foliation is space-time, but it's determined by the wave function. So the theory somehow it seems to me in a much better shape than it is. Like I said, my main interest at the moment is going the direction of quantum gravity. This is what I've been doing the last 2 years. Again, as a physicist, not as a philosopher. Okay, thank you.
On the view you presented, is the wave function a physical thing?
Yeah.
And
the way in which I present it is a physical thing, yes.
it's a physical thing, and it doesn't exist in ordinary space.
No.
So
It is a function of n-points in physical space.
So there's a configuration space which
No, there are n-points in physical space. Physical space is primitive. There are n-points in physical space, and psi is a function of n-points in physical space.
Okay. And then it's somewhere else. It's not in physical space, though.
Like I said, it's a function of n-points in physical space.
And then time evolution happens in both physical space and wherever the wave function is. Okay. Yeah. I just wanted to understand the picture.
No. Yeah. But I
these were
insist
genuine
on this point,
questions, not
because
not
in the years we had a
preparation
lot of arguments with David Albert. This is a theory in which he likes to present the theory in a different way. We present the theory in the way in which I just said. I start with physical space as primitive. There are n-points in physical space, and the wave function is a function of n-points. If a particle are identical, really n-points. If are non-identical, I should say, is a function of n-ordered points in physical space.
Okay, thank you.
Any other question?
Is there a simple way that the Bohmian theory can account for coherent states, which sort of at first glance are superpositions of different particle number? That's one thing I've had difficulty understanding how this would be treated in the Bohmian picture.
I will say that whatever good argument there is in books, standard books, I will apply to Bohm. Bohm is not, I want to make it clear this, I never use Bohm as a tool to make computations or as a tool to, except, okay, I did for a part of my life this application to chemical system in which you can use Bohm trajectory to do computation, but that was just an accident. Okay, in general, I don't think this should be thought as a good way of understanding what is going on. But most of the answer that you will give in classical, in standard quantum mechanics will apply here, will be the same nature. Will be different if you will ask me a conceptual issue like how happened that I have a wave function with several pieces and then only one is relevant. Okay, that is Bohm give you an explanation for this. But concerning coherent states, or say why a laser is producing coherent states, there's a normal textbook in physics. That's the answer that he gives you. I don't think the Bohm, for that particular question, will give a new insight. He gives you a new insight when you try to something more ambitious, like I hope that to get in gravity something new. I mean, my goal has been always to produce new physics, but not to produce new physics in small things where I know that the standard understanding works well. But those where the standard understanding doesn't work well, in normal quantum gravity, there are problems about time, diffeomorphism, variance. Here, I think the ontological clarity of Bohm is helping, and even is helping to construct a good theory. But my goal has been always to use Bohmian mechanics as a tool to produce new physics. As a physicist, like I said, I am.
I think this is related to Ruth's question. Can you just tell us a little bit more about these Bohmian versions of the quantum field theories? What are the beables for such theories?
Okay. Yeah. I don't have slides for that, so I have to use my hands. Okay. There we use the number of particles. If you're in a lattice in a certain site, or if you're in continuum, you have the density of fermions in a given region of space. That's what we use as a basic variable, which are bilinear in the quantum field. I mean, the corresponding operator are the usual psi, dagger psi, where psi are quantum fields. So for Fermi, while for boson field, you can use directly the quantum field and go into representation in which the field is diagonal and use that as a variable. In the case of Fermi field, the Fermi field do not commute a space-like separation, but the bilinear of the Fermi field, they do. So if you take psi star, psi, j mu psi, this sort of thing. So we take that as basic variables, and given, that's what we do, then Michael tomorrow will say something different. Given the particular structure of a Hamiltonian, you will have that this number cannot satisfy a deterministic equation, but will satisfy a stochastic equation. There is a lot of freedom in choosing a stochastic equation. By imposing equivariance, we reduce the, first, let's say, the Markov, impose equivariance, still there is a spectrum of possibility. We choose the simplest one. And the simplest one is the one that then we present in this work. But it's a stochastic evolution for the density of particles, which will be so in agreement with the quantum prediction for the density of fermions on a given space-like surface.
So these densities are, in the case of a continuum, they're continuous functions.
Yeah.
Yeah. What does a non-relativistic limit of that look like? Does it look like the theory you started with?
I hope so, but the non-relativistic limit of quantum field theories are usually tricky. So one has to be careful what, I would like to have a theory of n particles in the non-relativistic case. Yeah, but I think if you start with some condition on the quantum field theory, you fix the total number, whatever, you put some cutoff, then I hope, but I never did it, so I don't want to sell more than I did, you should get a normal classical limit.
So you mentioned the derivation of quantum statistics in the Bohm interpretation.
Yeah.
And that seems to follow up on the argument of Leina's and Murheim.
Yeah.
But the Leina's and Murheim argument works in standard quantum mechanics.
Yeah.
From the reduced phase space in classical mechanics, of course.
Yeah.
And so what's the advantage of the Bohm approach here?
So, two things. It's not exactly Linus and Murheim, the one that I gave with the covering space. It's different. You can have, but let's forget about this mathematical difference. No, I say that in the Bohmian case, it's much more compelling why you should use that configuration space. Then you can rely on many of the results that they get, mathematical results. But something that they don't do too much, simply because they didn't do it, is this study, a serious study of what happened when there is spin, and how to exclude parastatistics. This we didn't see in the literature. So this was proven by us in one of these papers. But of course, a similar argument for the exclusion of parastatistics you could get also in a standard framework. But the standard framework, I insist on this, is when people take seriously the configuration space. Very often in quantum mechanics, you can see, especially people doing quantum information, don't taking seriously the configuration space. These are topological effects of the configuration space. If you're in standard quantum mechanics in which you have a unitary equivalence between all of the representation, why you should take seriously the configuration space? Here you have a reason. I mean, here you have a well-defined reason.
I think there are reasons, and I agree with you that people should take it more seriously.
Fine. Good.
There's reason to even stand.
I mean, it's where the interaction are. The locality of interaction is just a normal space representation. Please.
You mentioned that all predictions of Bohmian mechanics gives the same prediction as quantum mechanics, standard quantum mechanics, for concepts which can be, which are well defined there.
Yeah.
Which hints that there are concepts which are well defined in Bohmian mechanics and not defined in standard quantum mechanics.
Yeah.
Do you have hopes that some of these things will be measurable, or it's just the only measurable things are those defined in standard quantum mechanics, and the Bohmian mechanics will not give us new things?
Okay.
Or you have some hopes that maybe some variation, whatever, or future theories, and we'll get something new.
Let me say, for certain things, I had hopes, and then I lost the hopes. Why? I mean, we studied for a while the problem of escape times, or sojourn time, or tunneling times. This, we devoted one part of our research to that. And of course, from Bohm, you get a very nice intuition on what should be the statistics when you are in a sort of mesoscopic regime, something which quantum mechanics doesn't cover. For instance, when let's forget mesoscopic regime, otherwise get too complicated. I want to answer. Yes, you get an intuition on what should be the statistic of this observer. But quantum mechanics is I mean, then at the end you can always fit everything in quantum mechanics. Why? Because if you use the generalized notion of observable, that means a positive operator valued measure, basically you can squeeze everything into that. So a posteriori, you can say, oh, but then a quantum person would use that positive operator valued measure, which you constructed with a Bohmian intuition, but you cannot claim that you cannot describe it in quantum mechanics, because quantum mechanics is very, I mean, the notion of generalized observer is so general that you can squeeze everything into it. And so you can squeeze also this Bohmian prediction. But you squeeze them, they don't appear natural. But okay, maybe there are other situations which maybe Bohm can give a better understanding.
Just Bohm himself hoped that it's just a step for new theory. It looks like the disciples gave up the hope.
I don't know. All my life was with that hope, and I still continue. Now I hope that gravity. Now it's many years that I'm getting familiar with ADM formalism, gravity, Wheeler-DeWitt. So I hope to apply these ideas there and to get something. New physics.
I have, if there are no more questions, I have one question.
Yeah.
And it's related, you mentioned that somehow in the traditional approach you have no clear cut between measuring apparatus and the system, and so it's always been a problem. And now you claim somehow that Bohmian mechanics solves this problem because you have definite things over there, but it turns out that these things are non-local. So there's a word full of non-local entities. And so now, which is the clear cut between these non-local entities and this word, which is completely local? I do not see non-local effects here, but there are some particles going on there that I cannot see, and they are non-local. Is there a clear cut between this non-locality and our everyday local stuff? Otherwise,
that has to do with the classical limit of this theory. That is a limit in which most of the non-local effects disappear. But you mentioned measurement. In normal measure, when I measure spin or Stern-Gerlach, in these cases, there is no non-local effects arising. And then, like I said at the beginning, quoting Bell, and here I follow Bell, and Lev will disagree with me, for me, quantum mechanics is non-local. So, because for me, that is a strong argument. Of course, that argument assumes that you have results have only measurement of only one result. But that argument sort of saying that quantum mechanics, any theory agreeing with quantum mechanics is non-local.
If there are no more questions, we take it.